everybody. I hope everybody's having a wonderful day. So I'm going to pick up from where I left off last time. So remember, last time I was talking about how we can compare different algorithms, and we talked about case-based analysis. So we talked about best case, average case, and worst case. These three types of analyses. The big idea was that I have some algorithm, and I want to measure its complexity. So this is either done by several different metrics, where you consider space and time, where space is the amount of memory we use, and time is the amount of time we use. Now, I haven't really said what time is. I gave you this notion how we can experimentally analyze the algorithms, but I showed you that there's some drawbacks to doing it this way. In particular, it was involving how we needed to actually have a clock, and we had the computers, and there was an issue of machine dependency. That's the big problem that we're running to, beyond some other things, ranging from restricted instances and so on. Now, in our analysis, what we're going to be doing for analyzing our algorithms is we're not actually going to determine the number of CPU cycles, because every one of our instructions in our algorithm, eventually on a tangible computer, now remember, I don't want to really tie everything down to just one computer. I'm not going to measure it in actual CPU cycles or the actual amount of memory on the computer. I want to keep the computer as broad as I possibly can while capturing and modeling what ultimately I want to compute. So measuring it by CPU cycles and the amount of memory, this is a machine-dependent approach to analyzing an algorithm. Remember, I want to actually analyze the algorithm itself, not the machine's implementation of that algorithm. That's the big distinction I want you to draw from what we're talking about here, okay? So we wanted to determine the time complexity, for instance, that characterizes the performance of an algorithm on all inputs, not just, oh, I picked a subset of them and I experimentally did. I want to do it on every single one. And remember, the problem is it could be literally a collection that is of size that's infinite. So I can't literally just run a computer that does them all, right? And I want to do it over all possible implementations of that algorithm. When I mean possible implementation, I mean you write up a program that is actually implementing literally what the algorithm says. Okay? This is not to be confused with switching out different data structures. Sometimes I use the phrase implementation there. This is a different context where I'm using this term. So this brings me to the notion of a model of computation. Now, before I get to that, I'm going to just motivate this by mentioning that really we're not going to be very particular on how we count instructions when it comes to our machines. We're going to, just as long as we capture things with respect to the input size, that's going to be our general goal. Remember, we established that the input size tends to be what scales with the algorithm's running time. So the larger the input size is, the longer the algorithm typically takes. So we're going to care about really certain parts of the algorithms, but you can literally just count every instruction, as I'm going to show you, but you're going to find that, well, I'll give you some motivation later, okay? So this brings me to talk about a model of computation. So this is a fundamental concept. So this is a formal model that describes computation as a hypothetical computational machine. So notice I'm not talking about just like my laptop, the thing I'm using to record this video. I'm talking about just an abstract machine that has some set of rules and how it computes those instructions, but when it executes the algorithm. So you might ask, and this is one way you can view this idea. I want to take you away from just one particular computer, one particular programming language, one particular operating system. I want to take you away from that entirely. Remember, I want to talk about what the algorithm's analysis is about, not its implementation. I want to try to capture it with some model so I can follow the rules of the model, and hopefully this model is going to be somewhat accurate to how a computer like your laptop would operate, but more in a mathematically pure way if you think about it. So you want to think about it, so this is one way you can view this. So I want to imagine if everybody had the same computer, the same operating system, the same specs, same everything. That's what our motivation is going to be by using a model. We don't have to talk about, oh, on his particular machine or her particular machine, it's going to do this well or this well, and you have to play this game of who's got the better specs or whose specs are buffering or causing inaccurate measurements of the algorithms. We want to stay away from this. We want to be computer scientists and look at this as I give you some computing machine, I perform an analysis for my algorithm, and on that specific model, it has this said time complexity. So I want to have a consistent and machine-independent model. So when I say machine-independent, my model doesn't keep me tied to one particular laptop. Doesn't, like if I use a desktop, doesn't matter. A smartphone, I don't care. So it's going to be a machine-independent approach. So I want to mention that there isn't just one model of computation. There's many that are equivalent to one another, but that's beyond the scope of this class. I'm going to keep things relatively high level here. If you're interested more in this discussion of models of computation, take a class like 356. There's a lot of discussion about different models of computation there. Likewise, 355 talks a little bit about this as well, but not to the same extent. But beyond that, there's all sorts of different machine models. There's pointer machines, register machines, counting machines. There's some other ones like Turing machines. There's many that are out there. But we want to use one that sort of models what you would imagine if you took a programming language out and wrote out an algorithm and you ran it on a computer. You want to use a model that's kind of like that. So this brings me to the random access machine model, or the RAM model. So the RAM model, if you're wondering, I'm not going to go into detail of how this model actually works as a hypothetical machine because of just the sake of time. But the way I want you to imagine this, now it's not going to be too overly crazy here. Imagine you had a mathematical set of rules that basically mimic assembly. And that's effectively what the RAM model is like. It's like assembly. So it's nothing too strange out there. So what we're going to do is I'm going to give you some rules for which we analyze the algorithms using this model. Now, while I'm erasing this, I just want to mention that there's many different kinds of models because we have different kinds of computational machines out there. The RAM model is a standard model that computer scientists, mathematicians, many people use. So it's somewhat informal in how many people use it as practitioners, but at the same time, it's also very theoretically deep, and it's equivalent still to some of the most powerful models, actually the most powerful models we know that you can actually implement, okay? So that's the great and rich part about it. So that being said, I got to tell you about what you could do under this model. So here are some assumptions. Some assumptions under this model. I'm going to lay out the rules for which we analyze the algorithm under this model. So the first thing I need to do is define kind of like an elementary operation. So what does that mean in our model? So we have some notion of what time is. You're going to find time is going to be corresponding to something that's like a step, one operation of sorts. So these are going to be what we call simple or primitive operations. Each primitive or simple operation takes constant time. Now, when I say that, I mean that it's independent from the input size. So I say, so that's independent from the input size. Remember, we talked about input size. So for example, remember, we talked about the sorting problem. The input size was n because I have n numbers. So constant, you think independent from the input size. So that means that I'm just going to mention, and this is just a consequence of how we're going to do our analysis later, we will treat these as one step. So for now, I'm just going to assume just some constant time. But later on, you're going to see that really we can just treat them like one step. And you'll have a better understanding of why this is the case when we get there. So such operations include the following. So a return statement. So a return statement, you're familiar with those. If I do a Boolean test, like if I perform a logical test that's just one of the very simple things, such as a comparison. So if I just want to check if something's true or false, like as in like the evaluation of a true or false statement, I'm just going to assume that that takes constant time. Now, remember, when I say that, I mean just like I give you two things, true or false, some logical operation occurs, that I'm going to assume takes constant time. So like an and, logical and, a logical or, not, these take constant time. That's what I mean. Let's say comparisons. So just to be clear, I'm talking about things like less than, greater than, less than or equal, greater than or equal, equals, not equals. And technically under the Boolean, but I'm going to typically assume arithmetic operations. Things like assignment. So remember, this arrow here, this is assignment. Just like when you assign a variable some value, that's assignment. Addition, subtraction, multiplication, division, and that's all of them. So I'm going to assume that all of these are primitive or simple operations. Now, you might naturally ask, if you're a little bit more inclined to involving systems, or just know a little thing or two, you might ask yourself, okay, well then, you've assumed that addition and multiplication, and even division, they take all constant time. Now, using your brain, you might think, okay, well, how exactly does that work? Because multiplication is like a generalization of addition. This is just an assumption I'm making with my model. I don't have to make that assumption. There's actually more particular versions of the RAM model that you might assume where multiplication is not a simple operation. Okay? This actually does pop up sometimes when you're doing your analysis where multiplications actually do matter a lot. So you might be a little bit more fine-grained and say, okay, this isn't a simple operation. But for the sake of our analyses, we're going to assume they're simple. Okay? They just take constant time. Okay, another thing. Subroutine. So subroutines and loops are not simple operations. These are comprised actually, I'll say composed, because I think that these are composed of many single step operations. So what I'm saying is that you can evaluate the for loop, assuming it has a constant number of conditions to check in the header of the for loop. You can do that in constant time. However, clearly all the iterations of the loop are not simple operations. You actually have to count how many iterations occur. So this shouldn't be too strange. The last one that I need to point out, actually, let's do a fun trick. Let's okay. The last one, and this one's actually quite important. I brought up this at some point. So each memory access takes, now technically I would say constant time, but I'll just say it takes one step. It takes one step. And as a part of that, the RAM model we can assume as much memory as we need. So you don't have to worry about some cap in terms of how many gigabytes you can have. There's no such thing in this machine. I can have as much memory as I need. Now you might ask, okay, well, Dan, these seem like, so remember, these are all the rules. So I'll pull up my pseudocode, and then I start looking and applying these rules to analyze the algorithm, okay? So the whole step is I get an algorithm, I understand the algorithm, then I do a case-based analysis to derive a complexity function. To derive that complexity function, I follow the rules of this machine, and then I can perform something with that. I haven't talked about that yet. Okay, so you might say, okay, well, these assumptions are not accurate, right? Remember, I told you that there's some drawbacks, like the multiplication addition problem here, are not accurate. It is, however, rarely going to give misleading results. So the great thing about this model is it's quite good at capturing your typical machine that has one core processor and it just performs operations sequentially. So if you have a sequential computer, this model is very good. So yet being so simple, it can be very effective. So we have a machine here that no matter how big the problem instance is, it should be able to take and handle it, okay? Likewise, I have a consistent set of rules that I'm going to follow for my analysis. So remember, it doesn't matter how big the input size is, this will work. So that's the big thing. This is going to simplify our analysis. It's almost going to be kind of deceptive. So let us return to linear search. So I'm going to analyze linear search. Now, before I get to that, I was going to mention something interesting to you. I talked about how each memory access takes one step. This is the prevention from creating a giant lookup table, because that'll take exponential amount of time. I create an exponentially large table. This will allow you never to have the worry of somebody breaking rules like that. Regardless, it makes sense that allocating memory should not just be something that you get for free, right? However, as much memory as you want, that's cool. So anyways, we're going to analyze linear search. So I'm just going to take one moment to just write out linear search again. You already have it in your notes, so you can even write the lines right beside this one, okay? Okay, there we go. Here we go. So here's linear search. I just for the sake of time, I didn't include the input-output. You already have that in your notes. So remember, I go through the loop until I get either a match or I is going to equal to n, right? So I've labeled the lines that get executed from 1 to 5. And what I'm going to do is I'm going to count exactly how many will occur in the worst case. So let's talk about that. Now, before I can do this, I need to identify the worst case scenario, right? So what's the worst case scenario? I'll let you think about that. We're going to perform worst case analysis on linear search here. So remember, we talked about this the other day, right? X is not an element of the array. Yeah, right? That's what the worst case scenario is. Remember, it has to do all these comparisons, right? It has to go through this entire loop. Because I have to check each and every one of the elements. So that's our worst case scenario. Now what we need to do is we're going to consider instances that look like this. And imagine we're executing the algorithm using these instances. So first I assign I is 0, and then I go through my while loop. I have while I is less than n, and else of I is not equal to x. Now remember, it's never going to violate this because x is it's going to always be where it's going to be not equal to x. So it's going to mean that it's just going to happen how many times? How many times? It's going to happen until I is equal to n. This while loop will check that condition, and then it'll say, hey, look, I'm done. The I is equal to n, and then it breaks out of the while loop. And then now we're going to consider the if statement, and you'll notice, hey, look, that if statement, well, I is equal to n, so I'd return -1, right? So that's it. So let's look at each one of the lines and count how many times it executes. So I is assigned 0. How many times does that happen? Only happens once, right? How many times does line 2 happen? Well, you know it has to perform n comparisons. So this happens n times. So it goes through n times, and then to escape out of the while loop, it has to check this condition one last time, right? And then it finds, hey, look, I is now n, and it says n is less than n, which is false, right? So it breaks out. So how many times? It's n plus 1. That extra 1 is for checking the condition of the while loop to break out of the while loop, right? Then, okay, let's think about this. How about line 3? Well, this happens only when that condition is satisfied, which was n, right? You'll find very often when you're doing this type of analysis that the lines inside the loops are more interesting than the conditions themselves to count. Then 4. That's where we get I is equal to n, and then we return -1. So I'll just say it occurs once. Now, technically, 5 never recurs, and I'm going to be overly generous and just say happens once. Technically, you could put 0 here, and that's perfectly correct. So I can put 0 here. That's cool. I'm just going to put 1 here. I just feel like being generous, okay? You'll see that it's really not going to make any difference. That's the point I'm going to make here. So what's the total time? Okay, to perform that assignment, the assignment has to take some number of CPU cycles. I'll call this C1. So it's 1 times C1. That's the amount of time it's going to take. So the point is I'm going to assign each one of these operations that happens here on a line. So how long it takes that line to execute, some constant that's going to represent the CPU cycles. Remember, I'm trying to encourage you that the CPU cycles don't matter at all. That is kind of my goal here. Okay, so second line, it's going to take some constant times n plus 1, right? The third line is another assignment here. But I'm just going to, for the sake of charity, I'll give it another constant, just in case, for some reason, you have a really strange computer where assignment just does not operate the same way. That is cool. This happens once, so I'm just going to give that C4. And this happens once, so I can give it C5. So this is so if I want the total amount of time it's going to take for this algorithm to execute in the worst case, it's going to be bounded by the sum of all of these. So the true time complexity is really just something that's bounded by this. So remember, I don't even have to have a C5 in here, but I'm going to show you that it makes no difference. This is so-called exact analysis, where I'm counting every single operation that's occurring by line. You can even count them by their actual operations, if you wanted to. I do it in the notes. You can take a look at that, and you'll find that I get the exact same results at the end. So it doesn't really matter which of these two you prefer. I prefer the line-based approach. I find it very natural to look at pseudocode and try to identify a certain line that executes the most. So that brings me to how we're going to talk about this. So I need to write something down. Constants C1, C2, C3, C4, C5 represent the actual number of CPU cycles. required to carry out the operations needed for each line. Now, I want you to observe that these constants could be different depending on the machine. That's the whole point I want to get at, is that these constants can be different. So I'm just pulling these out, and I say, okay, well, your machine might have different constants than my machine. The whole point is they don't matter. Unless you're doing some sort of experiment, that doesn't matter here, okay? So you can assign these actual values and say, okay, the assignment's going to take 0.2, somethings, and so on. You can actually assign these based on the machine you're interested in. So you can actually make estimates of the actual running times in the worst case by doing this kind of thing. So this exact analysis does have some meaning. So the total running time is equal to what? So I'm just going to sum up the total times. So this is C1 plus C2 times n plus 1 plus C3 times n, right? Plus C4 plus C5. I'm going to just do some rearranging. And you'll notice that I can say that C2 plus C3 times n plus what? I got to put everything else together. Plus C1 plus C2 plus C4 plus C5. I'm sort of running out of space. All the other constants are in here. Notice that I have an extra copy of C2 for that one extra line execution for the condition. So everything's here. Now, I want you to observe the function that this created here. What is that called? The running time is a linear function of the input size. They already see that. This is linear. So if I were to take this, you can see I can assign this to be some value A, and I can take all these constants and I can assign them to be some value B, and I end up with A times n plus B. This is a linear function. So the point here is that you'll notice that this is linear. And all I did was I just counted the number of times the line executes, right? And I just followed the rules of the RAM model. And I was even extra generous here. The reason why I did that is just in case, because some people like to think that the worst case of linear search is when you get to the very last position. That's also valid as a worst case situation. So I just put it in there. It doesn't matter. But the key thing is you need to clearly define what the worst case scenario is. You count up the number of steps, and you can simplify like this, and you get a function. But you'll see very quickly that and we're going to see this some examples later, is that I really just don't have to count all the lines. You'll notice that there's really two lines that kind of guide everything in our analysis, lines 2 and 3. All the other ones just take constant time, right? So it really revolves around this while loop. We're going to see that that's going to play a very important role in how we analyze algorithms. So I just want to mention one thing. I've written it in the notes. Just for the sake of time, I'm not going to talk too much about it. But I will just make a small remark here about comparing algorithms. So one thing I really want you to remember is that there are these constants that represent the CPU cycles, and they depend on the different machine that you're thinking of. That's at least one intuitive way you can look at these constants. Remember, I told you you could just treat them like one step, and you still get a linear function. So let's talk about comparing algorithms. Did you notice I did some weird trick here? I didn't even erase this board. It's some weird stuff, man. So we're going to consider two sorting algorithms. Two sorting algorithms that sort n items. So algorithm A and algorithm B. So their worst case running times so algorithm A is going to take approximately n squared operations. And algorithm B is going to take 50 times n times log base 10 of n operations. So these are their worst case running times. They're approximately this. So what I'm going to do is I'm going to look at how this behaves with respect to the input size, just to convince you that there's something interesting going on here. So I'm just going to take a moment just to quickly draw out a table. So I've drawn out the table for us. So I've labeled out the input size. I've clocked out how many operations are happening for each of the algorithms. So at first this looks like n squared. Then I have 50 times n times log base 10 of n here. I clock out algorithm A. You'll notice it goes up roughly powers of 10, which matches up with this. But notice it goes up by even. So I have 100, 10 to the 4, 10 to the 6, 10 to the 8, 10 to the 10. That's kind of big. Algorithm B, however, starts 500, 10 to the 4, 1.5 to the 5, 2.0 times 10 to the 6. And then lastly, for 100,000, it's 2.5 times 10 to the 7. Now, I want you to notice very quickly here that there's going to be some point n where these two algorithms basically are neck and neck. It's right about here, right? So right when you get to about 100 here. But notice right when I get to like 1,000, you can clearly see that this algorithm is all of a sudden just doing considerably better. So you'll notice that at this particular n, you'll notice that they match head to head here. But notice after this, that algorithm B seems to be better. Seems to be better, right? It's because you'll notice that n squared there, and this function over here, which is roughly it's log linear. You'll notice that these two have they're different functions, right? But you'll notice that up to some point n, you'll start to see the trade-off occur for a sufficiently large n. So there's two pieces I want you to keep in your head. These constants here that represent the number of CPU cycles, at least intuitively. They don't have to literally mean that. However, you'll notice that there's some point n where one of the algorithms is going to end up outperforming the other one, no matter what big constant you might have. That's the big point here. So even if I gave you a computer, now say let's go 10 times slower for, say, this one right here. This algorithm B, would still outperform algorithm A quite quickly. So I want you just to think about that. Likewise, I also want you to consider the idea that these algorithms could be heavily dictated by the data structure we select and how careful we might be when it comes to designing the algorithm itself, okay? So I want you to keep that in the back of your mind. We're going to talk about now so-called growth rates. Because you'll notice that it seems like we have to consider up to some sufficiently large n, and then the algorithm, we seem to be capturing the efficiency of the algorithm where we can really say definitively one is going to start being better than the other one. Likewise, you have all these constants around. I want to give you some natural way of talking about this. So give me one moment just to erase the board here on the left. So I've written up something on the board here. Yes, I did something funny. The point here is that I'm going to be dipping into the bag of mathematics called asymptotics or growth rates. So what I'm going to do is I'm going to define a very important definition that I will expect you to know. So I might literally ask you about what this definition is on a test or things like that. You need to know this definition. That's what I'm stressing. The fundamental definition. So I'm going to define something called big O. So you may have seen big O in a previous course, but I'm going to formally define it, and we're actually going to prove things about big O in this class. So here's the definition, and I want you to say it with me if it makes it easier to remember. So let f and g be complexity functions. F of n is big O of g of n. If and only if, remember that means that whatever's here is equivalent to whatever follows after it. So if and only if there exists some positive real constant c and a positive integer constant n0 such that for all n greater than or equal to n0, that particular constant n0, f of n is less than or equal to c times g of n. So I reiterate, this is an important definition. I would like you to carve out some space in your brain and remember this definition. It's going to be important. So just remember that f of n is big O of g of n, and this is one intuitive way to remember it. So remember we talked about the constants in our algorithm. Remember these are supposed to represent kind of like our CPU cycles, right? So that's what our C is. So I got to find this C, and I need to find this n0. Remember that's the point for which our algorithm. Remember this example over here. I found that particular n, where the one algorithm all of a sudden just started doing better and it absolutely annihilated the other algorithm, right, in terms of its complexity. So we're going to find these two things, and that's our goal. And if we can find these two things and prove that they satisfy this inequality such that when I pick these two, then we're good. So there's two big things I need you to remember when we think about the game plan for this. I need to find C and N0, and once I found them, I need to make sure that I satisfy that inequality for all these possible values of n. Okay? So I just want to make some remarks. So in terms of usage. So literally, oftentimes it's that f of n is big O of g of n. Other ways you can say this is f of n or f. Actually, I'll just say f is of order g. That's one way you could say it. F is of order g. Another way is f is in big O of g. I'll explain that one actually right now in terms of usage. So there's going to be kind of two ways you're going to find big O very useful. I'm going to illustrate both of them for you quickly. The first one alludes to what I meant in the second verbiage here. This is in business. Because the first thing you might ask is, okay, well, we've used big O before. We kind of just drop constants and all that stuff. But what is big O? So I'm just going to say notes about usage. So the first thing I want you to note is that f is big O of g of n, f is big O of g, is often written two ways. This is about usage, okay? So the first one is that oftentimes you write f is in big O of g like this, or you say f of n is in big O of g of n, where this is, in set theory, this means in. That's why I said over there it's in. Some people will write it this way. This is technically the mathematically correct way of writing this. However, you'll find it's not necessarily useful in all settings. Why do I say this? Is that big O actually is the following. Big O notation represents a set of complexity functions. That is the following. So big O of g of n, like I said, I'm going to abuse a little bit of notation here or there because it's useful. Remember, just don't do too much, okay? So g of n is big O of g of n is equal to the following set. So f of n such that, so this means such that there exists, remember I said there exists, this backwards e means there exists. There exists C in the set of all positive real numbers and 0 in the set of positive integers. For all, so this upside down n means for all. You can remember, you can just write out the words if these symbols look really strange to you. In a class like 277, you'll definitely encounter these. So we have there exists C and n0 such that for all n greater or equal to n0. And then I say, I need a little bit more space here because I'm writing a little bit big for you. Such that f of n is less than or equal to c times g of n. You're going to see how this representation is pretty useful sometimes. So you don't need to know what a backwards e is and the upside down a are. I really just want to show you this so you can see it. But yeah, it's just a set of complexity functions. So you're going to find that this usage is very useful in this mathematically rigorous way when we talk about a set. We're going to see how this is useful later on when I show you a proper example. Another way you can use it, now remember, I'm perfectly fine with you just writing f is big O of g. That's how I'm going to do things in this course typically, unless it merits it. So if you like one of these two, you can also use that too. If you just want to say f is big O of g, that's cool too, okay? I'll understand what you mean. Just be very careful when you use them in these particular ways. This way, you cannot use this notation when you're going to use this one below. So here's the following. So this is the other notation. So you might know this is f. We're having the equal sign right here. So I say f is big O of g. So where equal sign means is not equals. So I'm going to be sort of overriding what equals means here. So you're going to find that this is a pretty common convention in a lot of computer science lingo. But we need to remember that this does not mean equals. But I'm going to use it like an equal sign. So it's like an abusive notation. So it often is used very often because you can use it to simplify calculations considerably. So when you're reading the big O notation like this, with this equals business, where it means is, you should read the statements from left to right and not treat it like a literal equal sign, okay? However, it's convenient to use because we're going to assume that it takes on properties of equals with arithmetic or algebraic operations, okay? So oftentimes this is used to simplify calculations. For example, like this. For example, say that f of n is equal to 5n squared plus 30n plus 20. Now, some of you might know a little bit more about how big O works. You may have seen this in the previous course. We can drop constants, then you just take the dominant term. But I'm not going to take that as face value in this class. However, just for the sake of time, I'll tell you that this is big O of n squared. Now you see that I just basically simplified all of this over here, right? Likewise, I can give you g of n and say g of n is equal to 2n cubed minus 5. Which this function here is big O of n cubed. I drop the constants, I just take the dominant term. The dominant term is the one with the highest power, at least in this case. And h of n, I'm just going to take this function to be 4n, which this is just big O of n. Then The way I want you to imagine this, each of these functions represents a subroutine of your algorithm. So if I do this analysis for each one of my subroutines, and say if I did something in conjunction with all of them together, I then can perform my calculations much more easily. So then I could just say, so imagine that they all occurred in my algorithm, one after the other. Then I could write that as f of n plus g of n plus h of n, which this is just big O of n squared plus big O of n cubed plus big O of n, which now you look at these and it's okay, squared, cube, nothing, just add to the 1. So this is just big O of n cubed. Notice how simple this makes things. So you can analyze an algorithm. So imagine if that was the running time of one algorithm that it's used by your algorithm. Each of these is, you can simplify your calculations considerably by assuming these are kind of like algebraic operations you can do. But be warned, you need to be very careful. When you read this, you should read it from left to right, because when you go right to left, you're totally abusing the notation. Because remember, big O of n cubed here is a set of complexity functions. It means I could quite literally, if you were to go from right to left, I could replace these with other functions. And that means the equal sign is totally being abused. So some people view this as an abuse of notation. Because it overrides the equal sign. Abuse of notation, but commonly used. So it has a useful place. So this is how you typically use it. You'll find that in this class, we won't use this a whole lot like this, but I want to show you it because I want to show you a bunch of different ways of viewing these things. You'll find very often I'll approach this one, or I'll just literally use the definition and use the word is in this class. In an upper year course, I might use this one or that one. Okay, so I want to talk about one other point. So big O is an asymptotic upper bound. What do I mean by this? I mean for sufficiently large n that this will act as an upper bound on your input size. I want you to be aware of the following complexity classes. So complexity classes, these are just sets. However, you should be wary that class just means like all of them are the same type in this sense. The following classes of complexity functions. So I'm going to use order them by containment. So I'll use subset. So this means subset in set theory. What you could just think about it as, okay, if I have an asymptotic upper bound, that means if I give you any of these functions that are smaller than it in its asymptotic way, that means that all those functions are going to be a part of the larger set that consists of these as well. In short, I'm just going to go from smallest to largest of these typical ones we studied. So this one first, this is constant. We already talked about this earlier. So these are the constant complexity functions. Then the next ones we often look at. Now, this isn't like a complete list by any means. They go of log n. Notice I didn't write the base. You can oftentimes assume that I mean logarithmic in terms of base 2, but I sometimes will try to write the 2. However, you're going to find out on, say, at some point you're going to find out that that base doesn't really matter. It's just a constant. Next one, we talked about this. This is linear. So big O of n, this is linear. Next, we have big O of n log n. This is log linear. You might be familiar with this one for sorting. So for example, merge sort has the worst case running time of n log n. Likewise, linear, we see it with linear search. We're going to see an algorithm not too long from now that has log n complexity in terms of the worst case time. And you may have also seen big O of n squared. This is quadratic. It's quadratic running time. Now, all of these, along with this broader complexity class, where I have n raised to some constant c, this is referred to as polynomial. So this is big O of some polynomial, where I consider a constant c. So all of these are often regarded as efficient in a broad way. So if we talk about a tough problem, usually these are regarded as efficient. In contrast, there are three others that are a little bit stranger. So there's three more that usually get studied very often. There's big O of c to the n. This is where c is going to be a constant here. This is exponential. So this would be something like a naive brute force algorithms oftentimes have exponential time running times here. So this is constant. And this is constant c greater than 1. So obviously 1 to the n, that's not very interesting, but 2 to the n, 3 to the n. Then we have big O of n factorial. So this is factorial. So we're really getting out there. And then lastly, we have big O of n to the n. So these ones, you really want to avoid these if you can. Okay? I'm not even sure what the name of that is actually off the top of my head. The point I'm getting at is that we're going to see that we have a whole bunch of these different complexity classes, and we're going to try to solve different problems, and we can lump, based on the best known worst case running time, different problems into these different complexity classes. So we can talk about each one of the problems like it belongs to one of these key ones. There's other ones as well, but the point is we're going to try to classify problems based on these. So for example, linear search. Like if I were trying to solve that search problem where the array is unsorted, that search problem would be a problem with the best known linear time algorithm. Anyways, the point I'm getting at is that this is going to get kind of interesting. So I'm going to show you one quick thing and then we're going to stop here, okay? Showing that f is big O of g. So I want to talk a little bit about this. I'm going to consider an example where imagine I have f of n is equal to 2n and g of n is equal to n squared. So what I'm going to do, so let us chart both functions. Let us chart out both the functions. So let me make a chart. And I only got like a minute here, so I better do this quickly. So I'm going to have 0, 1, 2, 3, 4. So this side is going to be n. This upper part, that's just going to be our evaluated value, our value that we get out as input from our algorithm. So we get 2. I'm going to go up by 2's here. 6, 8, 10, 12, 14, 16. I kind of needed to fudge this a little bit. Okay. So I'm going to plot out these two functions here. Okay. So I know that if I consider 2, I should get 4 for f of n. And likewise, it should go up to 8 when it's at 4. Now, to pull out the dramatic meter stick, let's plot this out. I knew this would have some purpose. So that right there is f of n. How about g of n? How about g of n? G of n, okay, well, when it's 1, it's 1. When it's 2, it's 4, right? When it's 3, that's 9, right? It should be 9. And you know it's 16 up here. So watch me pooch this. So let's see how we do. Oh no, oh no, oh no, oh no, that's pretty bad. I didn't cross through one of the points. The point is that that's a quadratic. So, I apologize, I missed one of the points. The point is that I'm just charting them out, but you'll notice that I really highlighted one point here. So here's my two functions plotted out for some values of n. So you'll notice that there's kind of like in my chart that I have, sorry, my table, where I had algorithm A and algorithm B, notice I try to find that particular n value, such that regardless of what constants might be at play, there's going to be some point where g of n beats or dominates, that's the technical term, dominates f of n. It's right here. It's right here. So right at here might be an ideal n0. And if I were to pick something like c of 1, sorry, c is equal to 1, this might work pretty well. So I'm going to say from our chart, it's a pretty sloppy looking one. This chart, we can see that f of n is big O of g of n. If c is equal to 1, then we can find n0 quickly, right? What would be n0? Remember, c, so I have to show that f of n, so remember I have to show that f of n, which is 2n, is less than or equal to some c times n squared. If I pick c as 1, look at my chart there. What's n0? 2. So you might find that n0 might be ideal to pick as 2. So notice that after any point after 2, this inequality holds and we're done. So the goal is to find c and n0 such that that inequality holds for all n greater or equal to n0. Okay? So that's going to be the game plan. So next class, we're going to talk about how we can prove that f is big O of g. And we're going to do some examples, and maybe we might have time to show when it's not. Okay? So say thank you very much, and have yourself a beautiful day.